Okay, my bitstream is done. We'll view the reports. We don't have any timing issues, so we can move to the software. There's not much software, but we still need to do that. So we export the hardware with the bitstream. We'll direct it to a new directory, FPGA software. And we'll start the Vitis. We'll direct it to the demo FPGA directory. And we'll create an application project. We'll use our XSA. We'll call it Data Mover Software in Core 0, and we'll open an empty application. And we'll start a new file. We'll call it DataMover.c. Now this is a hardware project, but data that is coming from the hardware to the DDR is still, we need to invalidate the cache to see it in our software. So this is why we need software. Like always, we'll have the includes, especially the X parameters. We need to define the address in the DDR. We'll recognize that we have a DDR. Here it is. And it started 0. Now the lower addresses are for the software, so we'll start our memory space at 01000000. This is where we put our address, and this is the address we'll give to the data mover. Next, we'll have the main. The main is just a while one loop going forever. We'll use it in debug, so we won't really run it all the time. We invalidate the cache for the data mover for 1000 bytes, and we flash the cache for 1000 bytes, and we can do it all the time, so we just need it in debug. So we compile this. I will connect my board. And we'll start debug. We have our software, Data Mover Software ELF, and we'll start debug. we program the FPGA and we want to see the memory space of this address, so we will use the memory viewer for this address, and here are still junk from the DDR ramp up. Now we move to our hardware. We'll open Hardware Manager, Auto Connect, and we have our ILA and VIO. Now for the ILA, we want to see transaction when we use the commands. So this is the command we use the valid here. This is the stream to memory valid. Once it rises high, we want to see a stream to memory transaction, and here is the command for the memory to string command, the valid. When it goes high, we will trigger, and we will use an OR for this, and we reduce, so we will have most of the ILA, reduce it to 100, and we'll trigger it. Next, the VIO. The VIO, first we have the two errors. We see they are low. We hope to keep it that way. Now, as we said in the memory, we need address 01000000. So we'll add the address both for the stream to memory and for the memory to stream. Now for the stream to memory, I will initiate 100 bytes. If you remember, we use divided by 4 words, so it will be 40. We deattach this, cut it down to size, and move it here. Our ILA is working, our software is ready, and we can initiate a stream to memory transaction. And the ILA caught, we remove the transaction, and we can check it out. Here is the transaction. We see that we wrote the address 1000 with the 40 with the 100 bytes, and we see here the data generator. Oops, no, not oops. Like I told you, we start with a 0, 1, 2, 3, and the ready went down. Now the ready went down, the data generator froze because the valid is still up. So the data mover start initiating the transaction, but it needs some time, so we remove the ready. Then 4, 5, 6. Like we said, we have 100 bytes, so we end it at 3F. That's 40 words multiplied by 4. That's 100 bytes. We hardware people work with hexa, and we look at the memory space. It's still junk because we need to invalidate the cache. Once we do, here is the data from 0 to 3F, 40 bytes, 40 words, 100 bytes, exactly like we expected. Now let's flash the cache, and we still have the transaction, the ILA working, and we read, let's read less, let's read 80 bytes. and we initialize a memory to stream transaction. And here it is. Here is the command that we issued. You see again 80 as the size, the address is the same. Here the memory, here is the transaction performed in the DDR. Here is the read. We're reading, and here is the data read. Here, from 0 to 1E, we initiate 1F, sorry. We initiate 20 bytes because we asked for 80 bytes. We asked for 80 bytes. This is divided by 4, that's 20 words. And the data coming out in the stream is here. Here's the data coming out exactly like we wrote it from the data generator, but we stop here at 1F, 20 bytes, that's it. Now we can see the status. Here the status indicates that we are okay, valid, and you see that there's still two more words, one words coming out after the status is high. So if you want to address this signal for a busy signal or anything like this, you need to consider that the axis stream is still working when the status is high, and that's actually it. So we saw the data mover. So we understood how to work the data mover, both from the data generator to the DDR and from the DDR to the hardware. I showed you how to use Xilinx Example design, and even if we use source and we use IP catalog and custom here, we still have the example design. But when we initiate it, it will be gray because it's need to synthesize, and a few minutes later it will be available to you. Working with the block design we saw, we learned how to put a Verilog file in our block design using add model and not using the IP packager, which is more complicated. And that's it. And we transferred data from the hardware to our DDR memory, and for our DDR memory to our hardware. That's it. This is the data mover. We came to the end of this tutorial. I hope you enjoyed it. I did. I hope you find it useful. Thank you and goodbye.